All right, so let's do an example word problem that takes advantage of exponential functions and logarithmic functions. So that's going to come up in a second. I'm going to read it aloud to you. The population of Mexico was 102 million in the year 2000 and had grown to 127 million by the year 2010. Question A. Find an exponential model for the population of Mexico using the above data. B. Use your model to estimate the population in 2017. C. Assuming the model is accurate and predictive, when does it estimate the population will reach 200 million people? So this question is talking about the population of Mexico. So we're going to need a variable for that. And if we notice, it says that in the year 2000, the population was 102 million. And in the year 2010, the population was 127 million. Okay? So this is the information that we have. Now we can use a lot of different models to predict populations, but it turns out that exponential models tend to be the best in these situations and with some caveats and such. If this were a linear model, then you notice it grew by about 25 million per 10 years, so you would expect that in 2020, this would be, 152 and so on and so forth. But populations tend to grow faster as they grow larger for the simple reason that there are more people that are reproducing, so there are more children. So it actually grows in an exponential way rather than a linear way. So let's go ahead and let's come up with our dictionary of variables. So in this case, we need a variable for time. So this is going to be time in years. Now, we could go ahead and just say 2000, but why don't we make 2000 our initial year from the year 2000? Okay, so what that means is that rather than starting at 2000, the year 2000 corresponds to the year 0. Okay, so basically 2000 is 0 years after the year 2000, so we'll just let that be that so that the numbers are a little bit smaller. And likewise, that means 2010, that's not 2010, that's 10 years after year 2000. The other thing we're studying is the population of Mexico. So let's come up with a variable for that. So we're going to say that this is the population of Mexico in millions of people. Okay, now we didn't have to use the letter P, but if we're going to say population, alliteration is a good way to choose our variables. And we also throw in millions of people so that we don't have to write down a ton of zeros. In fact, both these choices are just to sort of cut down on the writing we have to do, because it would really stink for every calculation we write to write down 102 million people. So this way, what we do is we basically don't worry about writing down these 6 zeros, possibly more. And we should also keep in mind that when we're estimating populations and we're estimating things in general, these models aren't 100% accurate. They're just trying to give us a good sort of guess for what's going on. And so we want to just be within some range of accurate. So if we think about this, if we're thinking about things on the order of millions of people, if you're off by 5 people, that's not really a big error. If you're off by a couple thousand people, that's a lot of people in some senses, but for a population for a country as large as Mexico, that's not that big. So we're going to go ahead and just scale down to that level. Okay, so if we do this, we don't need to write down all those zeros. So the first part is it asks us to do an exponential model. Now an exponential model typically has the form P of t is equal to P sub 0 e to the RT. Okay, where t is our input, P is our output, and then P naught, E, and R are different variables that we'll need to figure out. So P naught is the variable that we're going to solve for. It's one of the parameters we need to make this model fit. So a parameter is just a variable that will be fixed at some point when we match these types of equations to this information. Same thing with the R. That's going to be used to match the information to this model or this model to this information. E is the constant 2.17 or 2.71 ... The reason we use E is that this is actually a very nice number in calculus settings. And so it's good to get comfortable working in this one. So now we need to actually solve for this model. And if we look at what these two sentences tell us, this tells us that if we set the year 0, that means it's in the year 2000, then the population is going to be 102. And in the year 10, we get 127. So this function, or this model, is basically taking its input, the year we want to check at, and then it's giving us as our output the population. So what we do is we just substitute this information in and try to solve for things as best we can. In this first case, this one's nicer. Anytime you see a 0, that's usually a sign that's the first thing you should be fitting. So if we plug that in, we'll have P of 0 is equal to, in this model, we're going to have P sub 0, E to the R, and then in this case, the T is 0, so we're going to put that in, and P of 0 should also be equal to 102. So we're going to substitute 102 over here. Now, if we do that, we have R times 0 is 0. Anything to the 0th power is 1, so we get that P naught is equal to 102. And so that tells us that this is the first parameter that we solve for. That is, we plug this in here, it's just this value. Now, this is just a nice feature of exponential models. That is, if you set one of your data points to be t equal to 0, then the output is just going to be this coefficient here, and you can see why there's a subscript 0. It's because it's exactly p of 0. So now we need to solve for r, so we're going to plug in the other point to figure that out, and we'll notice that p of 10 is equal to p naught, but we know what p naught is, so we can substitute that in, e to the r, and then in this case, the t is going to be 10. So we put that in. And that's supposed to be equal to 127. So now we need to solve for r, and we'll have figured out our model. And then at any point we choose a t, we can find the p and vice versa. So we're going to divide both sides by 102. So we get e to the 10r is equal to 127 over 102. This is an exponential equation, but the variable is up in the exponent, so we're going to convert it into a logarithmic equation. That'll give us 10r is equal to natural log of 127 over 102. Divide both sides by 10. I'm going to move over a little bit. R is equal to 1/10 natural log of 127 over 102. Now we can go ahead and plug that into your calculator to actually get a decimal number. And so this is going to be approximately 0.02192. Okay? Now it keeps going off and on. What I would suggest is just keeping maybe 4 digits or so. It's all a model, it's just an approximation. So then this gives us our model. It tells us that if I want to find the population of Mexico in millions of people in some year t, that's going to be equal to 102 e to the 0.02192 times t. Okay, so in part A, we actually found the function that estimates the population of Mexico based on this information. So this is a model. And what that means is that it is a way to accurately guess mathematically what's going on. Now, it is a model, which means that it's not 100% accurate. In fact, a lot of things can happen to make this model inaccurate. But what it's doing is it's telling us that if things are proceeding as they have been, this is what you should estimate should happen in the future. All right, so now we're going to use this function and model to go ahead and do some predictions and do some estimates. So first, the second part of this question is part B. It says find an exponential model for the population, use your model to estimate the population in 2017. So if we look at that, we need to figure out what's going on in 2017, and we need to find the population. Now, if we think about that, what that means is, well, 2017, we don't plug in 2017 for t because it's in time and years from 2000. So it's going to be 17 years. So in this case, this tells us that the t is 17, and what it wants us to find is p is 17. So now we just substitute it into this model and see what comes out. So p of 17 is going to be equal to 102 times e. Now, it's a good habit to put everything in the exponent in one big parenthesis. So we're going to do that. So 0.02192 times 17. And if we plug that into our calculator, we'll get approximately 148. So what this model is telling us is that based on the information we have from the year 2000 and the year 2010, it should tell us that if we were trying to figure out what the population in 2017 would be, we would expect it to be about 148 million. Okay, so it's grown about 21 million since 2010. And so if you want to, as a side exercise, you can actually go look up the population of Mexico in 2017 and see how accurate this is. It might be close, it might not be. So now that we've done that part, we might want to flip the problem a little bit. So let's go ahead and let's look at part C. So assuming the model is accurate and predictive, when does it estimate the population will reach 200 million people? So what it's asking is, what t has p of t equal to 200 million? Okay, so let's just write this down a little more grammatically correct. So what this is asking is, instead of figuring out what the population will be in a certain year, it's asking us how many people we should, at what point should we expect this many people? So what we do in this case is we just simply plug 200 in for this and solve for t. So we get 200 is equal to 102 e to the 0.02192 times t. So now what we need to do is solve for t. So this is just algebraic exercise. Divide both sides by 102. Now we need to convert this exponential equation into a logarithmic equation. And now what we need to do is just solve for t by dividing both sides by 0.02192. So if we do that, that'll give us 30.7. So that's telling us that if we want to know when the population will hit 200 million people in Mexico, this model is going to estimate for us that it'll take 30 years and then 7/10 of a year. So if we wanted to be a little more accurate, even down to the month, what we could do is take 0.7, so it's 30 years and then 7/10 of a year. A year is 12 months. We multiply that by 12. We get 8.4. And so what that tells us is that it's in the 8th month of the year. So then if we were to actually say when this had happened, so we predict the population will be 200 million in August 2030. And so that completes the problem. And so now we've basically figured out that if we want to figure out when we'll hit 200 million people, and if this was like the government of Mexico and they needed to do some estimates on housing or other resources, this is when they would expect to sort of be ready for about 200 million people. So all in all, what we've done is we've taken a bit of information about a population, we've used the right model for population, which is an exponential model, and we go ahead and we fit that model to this information here. And then once we fit this model with this model to this information, we can now use this to predict things about what we expect to happen in the future. And what we did was we estimated the population in 2017 so we can actually compare it and see how close it was. And we can also use it to estimate basically when population will hit a certain point.